Thank you very much for the opportunity to come and speak to you about some reflections on astrophysical software development and lessons that I would say I've learned and some thoughts for the future. My name's Phil. I mainly work on Swift, as you've heard, because I mentioned it earlier. For those who don't know, because I'm not really going to say much about it in detail, but Swift is it started its life as a gamma ray burst observatory. It's now a kind of multi-purpose TDAM, time domain, multi-messenger, and anything else you could think of observatory. And I work on the X-ray telescope, but really I'm going to be talking about stuff from the software perspective. And I thought I'd start off by saying, why should you listen to anything that I have to say on this subject? And the answer is you have absolutely no obligation to. You're welcome to doze, snooze, preferably don't snore too loud, or reject everything I say. But the position from which I'm coming from is, you've already seen this, but at least I get to show you the movie just because I like non-static things in the bottom. But I've been working in astrophysical software development on and off for something like 20 years now, which makes me feel extraordinarily old. My youngest child has just gone to university, so I feel ancient. But yes, and so that's kind of where I'm coming from to give this jump on to give my thoughts. So I'm an X-ray astronomer primarily. That's where I started out, at least. And I've been writing astrophysical software for a long time. So I did my undergraduate degree. It was actually a dual honours degree in astrophysics with computer science, although I dropped the computer science part after 2 years because I didn't like computer science. I didn't like Java. And various bits about it. So that was at the University of Kiel, where I then did my PhD. But in 2006, I joined the Swift satellite team as a data center scientist. And then in about 2014, I became the sysadmin as well, because we got a decrease in funding and we couldn't keep a separate sysadmin. So I reckon that means I can call myself a full stack developer, which seems to be a kind of cool thing now, because I do the Linux sysadmin, the virtual machines, the databases, the mail server, the batch processing queue, the software on the front end. So there you go. I call it a jack of all trades, which means I can just about cope with doing bits of all of them, but I would never like to be considered an expert in any of them in great detail. I took over leading that project. And then I put this at the bottom deliberately because one of the things to learn is that I'm supposed to, several years ago now, I've been handing over control of a lot of what I've done to somebody else, and that's taking a lot longer than intended, which is entirely my fault. It's largely because of this thing called documentation. I don't know if you've heard of it. I haven't. But also, I'm now the technical lead of one of the instrument science centers for New Athena, which is going to launch eventually, probably. And so I find it quite interesting doing a bit of a retrospective on my experience so far, just for my own sake as well. So to give, again, just the context of where I'm coming from, those of you who have the slides uploaded, I'm going to whiz through these next few slides really quickly because they're not massively relevant, and I realize I'll run out of time if I don't. But it's just an overview of where I am. So my kind of goal and work has been focused on building automated or on-demand tools to get what I call science-ready data products. So that is pipelines that do all of the definitions of your source extraction, your background extraction, all your instrumental corrections, things like pile-up, which is a big issue in X-rays, all applied for you. And to do that, when I say science-ready, it should be at least as good as what an expert can do by hand, which it turns out in most cases it is. And as you've just heard, you know, for something like the Vera Rubin Observatory, or a square kilometre away for that matter, that are going to produce these just stupid quantities of data. I mean, I can't get my head around the data rates. Good, automated, really reliable science pipelines are vital because there's just no capacity to do everything manually. So I actually started off my life just being asked, well, not literally my life, but, you know, being asked to produce automated light curves of gamma ray bursts. And I figure this just shows some of the challenges in the X-ray regime. For a gamma ray burst, this is 6 orders of magnitude in brightness it covers. We've got some that are more than that. We've got 3 in different colors, 3 different modes that the instrument takes. And of course, your binning is going to want to vary because of the brightness, and a handful of other problems that kick into there as well. All these orbital gaps, because Swift keeps slowing off and coming back and doesn't point quite in the same place each time, and so on. We don't have air mass to deal with, at least. I didn't realize that was a problem for you optical people. There's no air where we are. Well, apart from the stuff that's making us deal with it, but let's not talk about that. You can do it in luminosity now as well, and spectra, some ways of improving the positions. A live catalog, this is something that I think is kind of cool. I encourage more and more of this kind of thing, that actually instead of building catalogs statically every however often, we can, all the tools that go into building a catalog, this is allowing us to compare one GRB with another. They exist. So this catalog's updated in real time. Got ways of comparing all the different instruments in Swift. And source catalogs. So again, I've done 3 of these, but this last one with an L. Oh, my pointer, sorry, doesn't appear. There's my. Okay, there either. There. The L means live. So our source catalog. This table is wrong because I made it a week ago. Well, 4 days ago. So that all of the numbers on here have changed since I did that because we keep this source catalog up to date all the time as well. And the idea just being to enable, Swift is a fast response satellite. So let's enable fast response science. And actually that gives us a real-time transient detector. So basically every time we find a source, and here's one, we say, could this be a transient? Is it known? Is it unknown? How bright is it? And so on. And actually what was really exciting is within a few months of turning this system on, we discovered a type of object not been seen before. And then the other thing, again, just behind where I'm coming from, has been this idea that you can analyze anything. Now, in the Swift context, anything actually just means point sources because we don't have an extended source infrastructure because it was outside our original remit. And I'll put a disclaimer in that really extreme cases don't always work. And I'm always surprised by how well they do work, actually. But you can do that by just literally you fill in a web form and you press go and you get your products back. Or you can use our Python API and you can do something like that. I'm sure that makes perfect sense to you reading a screenshot on a screen. My undergraduate students, no matter how many times I tell them, they still think the best way to ask for help with their coding course is to take a photograph of the screen and send me their program instead of just copying and pasting their code. I mean, So yes, I can compile your screenshot, thank you. But you can then get images like this down and so on. And the reason I've been a little bit distracted, oh yes, sorry, this gets used a lot. The reason I've been a bit distracted this morning is the whole site's down today because I've just discovered that our SSL certificate has expired and I didn't get the usual warning notifications to the desk when I'm trying to get that sorted out. So I apologize if anyone's trying to use our tools today. So that's where I'm coming from. Let's just move on to the real focus of what I was going to talk about, which is what will be my reflections and advice and thoughts and lessons learned from all of this. And the first thing that I realized when looking backwards on Swift and looking forwards to New Athena is just how much technology has changed. So I put the dates at the top there. From 2006 to 2021 was when I was just a data center scientist. And to start in 2006, if any of you can remember back that far, I just joined the Swift team. I had an excuse to get broadband internet because we had to respond to gamma ray bursts in real time. It was like a luxury to get something that wasn't dial-up. It became mainstream not long after that, but it was still somewhat on the more expensive side. This really made me laugh. The typical server, right, a dual-core CPU with 4 GB of RAM. I've just bought new hardware. Our servers have got 36-core hyper-threaded CPUs, 72 threads each, with 196 GB of RAM. And we've got solid-state disks and stuff in there. You think how much that's changed. Flash, do you remember that? Yeah, and Java applets. Seriously, at university in 1999, the first thing we learned to do was write a Java applet. Yay. People thought IDL was a good, sorry if any of you still do. I'm sorry more for you than to you, but and so that's kind of where we were. And there's plenty more about 2006 I could say. But if I just look at what's happened in the meantime, we didn't have smartphones. The first iPhone was 2007, then Android. 4G mobile, look, 11 UK cities, how exciting. But 4G mobile internet. Some of the technologies that are used a lot now, Docker, Astro-COLIBRI, we're still, I mean, this is actually now a decade or more ago, but it's, new things, Kubernetes, oh, how exciting. 5G internet, and of course, Python 2's end of life, Java applets have been deprecated. The amount of change that we've seen in both the tools that we use and the infrastructure we use them on is huge. And if that's 19 years, and New Athena, for example, I'll just pick on that because it's what I work on, has got 13 years to launch. What's going to change between now, where we're thinking about what our software should do and our infrastructure should look like, and the time we actually turn it on, never mind the time that we actually turn it off. And so, in a sense, my first reflection and piece of advice that I give, and again, if I'd known what was going to happen and where all the stuff that I did was going to go, I'd have taken this seriously myself 20 years ago, is assume essentially that your infrastructure is going to change. So design your code to be infrastructure agnostic. So that could be, for example, using modules and classes. To give maybe a silly example, forgive me if this is slightly technical, but it's not that silly an example. So when I joined the team, I was told you need to know Perl. Some of you will wince at that. I actually still quite like Perl a lot. I am Pythonizing myself. But anyway, so I have about 600 Perl scripts, and they execute sub-processes by using the system command. If I was the Python scripts I've written, they do it using subprocess.run. And that's fine. But what if one day we decide we don't want to just run things in a subshell, right? We want to fire them off via something asynchronous, like a Kubernetes container, or subprocess.run breaks, or I don't know what. If we'd written just a little lightweight module, like with a single function that takes a command, its options, standard input, and returns an exit code, standard output, standard error, and use that, then when we want to change from using the current whatever it is you use to submit jobs to using something new, you have to change that one module, not 650 Perl codes. And that sounds obvious, but even at the level of executing codes, I point it out because, well, I certainly need to learn that lesson. Yeah, we've changed our batch processing system 4 times, and it's been painful every time. The other thing to note, though, is scope changes, and this will happen. I would almost be tempted to say that if the scope of your project doesn't change, something is wrong, because of the nature of science, right? We're always pushing at the edges. So I arrived at the Swift team. My actual boss was off on sick leave at the time, so the stand-in boss, who's ironically now my academic mentor, just showed me a piece of paper, and he said, this is what we told the funding council would do, that's what we're paying you for. And it said, build automatic XRT light curves. So, okay, that's what I'll do. And then a bit later, after doing that, my other boss came back and said, could you take this work we've been doing to improve the positions and kind of systemize it and automate it and take it a bit further? So I kind of did that, and then thought, how am I going to I need some way of hacking so that both of these things kind of run at roughly the same time, and so on. And then we came up, well, wouldn't it be useful to have spectra as well? And then someone says, well, actually, if we're doing spectra, we can make flux corrections to the GRBs, the light curves, so can you add that in? And then we got this point where we were saying, well, this is great, Phil, thanks. But sometimes when we detect a gamma ray burst, we don't know which X-ray source is the afterglow. Sometimes we didn't detect it, maybe another satellite like Institut did. And can you do something to help with that? And so I did. And that was great. But then people didn't like the fact that when they decided which one was the afterglow, you had to ask me to go and type in a load of commands to change it. So can we get that working through the internet? So I can click a button and make that happen. And then this thing comes along of, what about when we first get a gamma ray burst and we all get out of bed at 2 o'clock in the morning? Wonder if any of these tools could apply to that as well. And so then you try and adapt them, and then that also goes back and feeds into your information from earlier on. And then people start saying, oh, can I use this to analyze my non-gamma ray burst data? And then multi-messenger happens. And ultimately, I started out life, and if you're at the Astro Audace conference in February, apologies, you've seen these slides, but I started out life, I felt like doing a little hobby job in my garden shed. Okay, which was these light curves. And then I'm not very good at artistic-y things, so just bear with us. But I came in and kind of plugged something else into it because I was asked to, and I ended up with this kind of similar but not quite the same association of kind of random bits of kit that were all built semi-independently, but also kind of running off my garden shed. And then as things grew and I had to power them in different ways and find better infrastructure to make them work, I've got this hodgepodge of power sources, and suddenly I'm running a metropolis on what's basically a garden shed, and I'm terrified to touch anything because sooner or later something's going to go bang. And that's really, that's not really too much of an exaggeration. That's not a good situation to be in. And that's because, I'm going to say it's because I was young and naive rather than an idiot, but I had no idea when they said to me, can you build these light curves, that this was going to open up this whole path. But that is the nature of science, and we should embrace that, I think. Because the reality is science changes, and science should change. I was at a conference in Cape Cod. It was one of the GW Paul ones. And I think it must have been 2016, because it was before the famous detection 1708-17. And someone had presented a list of what the questions are that LIGO and Virgo and Kygo are going to answer. And I remember Alberto Vecchio from Birmingham standing up and saying, this is great, but if that list is all that we find, something's not right, because we should be expecting to find the unexpected. We're doing something brand new, we should be expecting to break new ground. And I think that's absolutely true. And if you're involved in any form of astrophysics software development support, we should expect that things are going to come along that we didn't expect and that we're going to want to adapt to. For Swift, I think the biggest, from my perspective at least, the biggest impact of this was when we started doing multi-messenger astronomy. And they started with neutrino doublets from ice cubes. So this is where you say we've detected two, well, flashes of Cherenkov radiation, I guess, but two presumably muons traveling faster than the speed of light, correlated in space and time. And you expect that from atmospheric background, but you can quantify it and say the probability of this being from the background is, let us say, 0.003, as in sorry, yes, that's right, 99.7, 3 sigma. Therefore, yeah, there's a 3 sigma chance this is coming from a real neutrino. And so we could follow those up and see if we can find any EM counterparts. And then, of course, as I'm sure you know, IceCube started detecting these high energy neutrinos. We never found a doublet that we believe was real. We did find some high energy neutrino. IceCube have found plenty of high energy neutrinos. We've had Antares alerts. I think we're now in the 6th year of writing our Swift follow-up for neutrinos program, saying we've been assured that KM3net public alerts will start in the spring. I kind of feel it's a bit, I don't know if anyone from KM3net here wants to update me, but it's a bit free beer tomorrow. It will come. And the good news is actually that stuff, when our SSL certificate is working, is live now. But it's a challenge for us because the Swift was designed to follow up its own gamma ray burst detected by BAT. It's built in its burst alert telescope. So we have a field of view big enough to look at our error regions, whereas this orange circle is a typical IceCube error region that we're getting. And so we have to innovate. And the operations team, and a huge amount of credit has to go to my colleague, Jamie Kenner at Penn State for this, finding new ways of making the satellite work so that we could do this mosaicing. And that brings another data analysis challenge from an X-ray point of view to actually trying to identify the counterpart. So we start to adapt and build new tools to do that. And then from our point of view, we had fast radio bursts. No one in 2006 knew that those were going to get discovered, obviously. And gravitational waves come along. And for those of you who have somehow not picked up on any of this, gravitational wave follow-up's slightly challenging. Because if doing a 7-point tiling for neutrinos was a problem, gravitational wave localizations can look like this. Now, I discovered about a year ago that I have ADHD, which explained quite a lot to me. I think Swift is also in the undiagnosed ADHD category because it can't sit still. And Swift observes typically about 70 fields a day, right? Which is quite a lot for satellite. But it turns out you can do even more than that. And this was an event from the 27th of February, 2017, where we did, you can see there, with Swift in 48 hours, we observed 1,408 fields. And I think even for like an small optical telescope, that would be a lot. For satellite, that's ridiculous. And as a data analysis challenge, it was interesting. The real problem from my point of view, and thinking about astrophysical software again, right, is I realized none of what we developed would really cope with this situation. So I had to write a new approach to the data analysis. And then having done that, I'm like, do you know what? This is so much better than what I've done for neutrinos and for gamma ray burst that didn't trigger Swift and for a few other things. I ought to try and apply this, like go and apply this to all those as well instead of the old software. But then you think, come back to here, and I've made some changes. And I'm thinking, I think that this old tool I can remove now, or can I? And you start doing a grep in the source directory to find out if anything calls it. And I end up feeling like I'm sitting in a room that's on fire, desperate to know if I dare unplug this wire, if it's going to put the fire out or cause the whole thing to explode. I still don't know. What I've actually done is I put little commands at the start of some of the scripts that send me an email if they run. I figure if I don't get an email for 2 years telling me that script has run, it might be safe to turn it off. Don't know. Even more fun has come about recently, again, just showing the nature of the challenges for what seemed to me like good logical design reasons. Things like neutrinos and gravitational waves and fast radio bursts and gamma ray bursts have been kept distinct. They use the same software. I haven't copied and pasted the software. I'm not quite that stupid. But they have their own separate areas, their own contained databases. It's controlled to a configuration file. So it's fairly easy for me to add another one of these. I call them mass tiling, but whatever, that doesn't interfere. I think that's great. And then SVOM and the Einstein probe launched. And SVOM and Einstein probe are fantastic, and they're finding new transients. And again, my colleagues at Penn State have done this great job of what we call urgency zero, target of opportunity requests. So what happens is, let us say SVOM Eclair detects something, and it puts out a GCN notice. The GCN listener at Penn State receives that notice and automatically puts in and approves a target of opportunity request. automatically schedules it and can upload it within minutes. I think the quickest we've been on target is something like 69 seconds. Someone will tell me, I'm sure, if anyone's online and knows I've got that wrong, I'll get corrected. But it's something like 69 seconds is the fastest we've gone from a trigger to follow-up, which is pretty sensational. And we don't know what those triggers are, and they can be all sorts of different things. So there's a SWOM area of our website, there's an Einstein probe area of our website. Only it then turns out some of them are gamma ray bursts, and so they want to somehow move from there into the GRB system. And to say that that's gone wrong about 50 times so far would be the polite way of putting it. Those of you who've had GCN circulars from me that have broken links in them, for example, I do apologize. Just as a side issue, it's not my lessons learned, but about, you know, IT services people sometimes making decisions that aren't helpful. All the emails we get in now have Microsoft safe links applied to them, which is demonstrably, sorry, but provably easy to get around and not very helpful. All that training you remember about check the URL actually looks correct. Yeah, you can't. So I get circulars that my system produced sent to me, and I don't know what the URLs are because they're just all jumbled up nonsense. I didn't realize they were all wrong. Yay, thanks, Microsoft. But again, it's just this, oh, how do you merge? How do you keep on top of things? So I would say two big things that I've learned, I'd pass on. It's so easy to skimp on the documentation, right? To feel like I've got to get on with this. I've got to get on with this. I'm not going to gain anything from spending half an hour documenting what I've just done. You'll save yourself months of work by doing that. And the other thing is to build and maintain a full test harness. And again, I wish I could go back and design this from the start. I want to know what happens if I pull this wire out. If I had a complete full offline system, I could pull the wire out and run it through the test harness and see what happened. Yeah, I didn't. So if I could start again, I can. I've got a chance to design a new ground segment from scratch. What are the lessons that I think I have learned, and what are the lessons that I would want to pass on to anyone else just starting out in this? And as I say, you know, these are my views. Others might vary, and you're welcome to say, Phil, this was obvious, or indeed, Phil, we don't care. But I'm going to pass them on anyway, because that's what I was asked to do, and it makes me feel important. No, so seriously, I've mentioned these two things as we mentioned in line, but you know, thinking about separating out the idea of what your code is going to do from what the technology is going to exist to do it on. Within Athena, actually already, some of the discussions have been, well, should we let people have the software that they can run it on their own laptops? Well, which a lot of us say yes. Or is it all going to be in the cloud? Or is it all going to be done through mobile phones? Or what? And of course, the answer is, how about we don't build a front end yet? Maybe we'll just leave the front end until 2035, 2036, when we have a better idea of what's going on. But we need to make sure the back end, therefore, is kind of agnostic of this. But actually, I think a good place to start and to take the time to do right from the start, is say, what is the end goal? Right, when we're building astrophysical software, because we've all got our ideas, it's easy to get really zoned in on what you think would be really cool, at least it is for me, and oh, this would be awesome. To stop and say, what is the actual purpose? And I hope I can say without controversy that the purpose surely is to maximize the science return. That's really what it's all about. And don't lose sight of that. That's what we're really here to do, is to ensure that the best possible science can come out of it. And the ground software, the science software, so ground from a space point of view, but analysis software, I feel sometimes gets a bit overlooked in this. I hear at the moment, like within New Athena, people talk about the requirements on source sensitivity and on how many sources we're able to detect down to the confusion limit and so on. And they're all focusing on the hardware and the optical PSF. But I can tell you that we've run simulated images through lots of stuff, and none of the source detection algorithms or software that exists at the moment are capable of actually getting the performance that is required. So without the software, no matter how good your hardware is, we won't be able to achieve the science. So it's important to recognize, and I'm preaching to the choir in the room, I realize, but you know, we're important. But at the same time, that software, therefore, to me, has to be something that allows scientists to focus on science. It shouldn't be something where I really hate it. There's always going to be a bar to entry for anything, but I hate it when you're trying to analyze a bit of data from somewhere and you're spending all your time trying to get this stupid tool to run, or you're trying to understand this weird instrumental effect. And as far as possible, what we want is a scientist who's finally got the data and probably is quite busy to be able to do the science. It should be understanding the data and interpreting it that's the challenge, right? Not actually getting it into the format that you want. And that sounds obvious, but it's not always easy. And I mean, good grief, you listen to the talk we've just heard and you can see some of the challenges in there. But there are problems because data analysis can be complex. Data can be esoteric at times. Problems aren't easy to spot. This is a real example from something that I think was embarrassing for everybody involved. I was at a science conference and someone presented this light curve. I think this is Markarian 421, an AGM. And they said, hey, look at this. This is really interesting because you can see all of these weird dips and flares going on in the data. What on earth is happening scientifically here? And then somebody else in the audience said, which was embarrassing for the first person, yeah, but they all occur at the start of an orbit. Doesn't that suggest to you that there might be something instrumental going on here? It's quite embarrassing for the Swift team to have that happen as well, but this doesn't happen very often. No one had reported to us this issue. That's entirely, it's not a software issue, it's the satellite is still moving as the observations start. It's still moving slightly. There are some dead zones on the CCD because we got hit by a piece of dust. And if as you're moving, your source just drifts across that dead zone, once it's settled, you think you know where your source is, you're not correcting for these. I mean, that's a kind of very specific example. The point is, once we knew about that, we were able to fix that in science, in software, but it's really embarrassing when people start doing bad science with your data. None of us want that. At the same time, I think we should make the bar to using data as low as possible. There are drawbacks to making the bar to using your data zero. I might come back to that. We'll see how we get on. But if you make it too easy to use, you can get people do bad things with your data. So how do we go about ensuring that what we do actually maximizes the science output from the mission? There is no like golden, this is the golden silver bullet. No general solution to everything. But I would start by saying, actually, we need to focus on the users. Sounds kind of obvious. I know users are annoying. When I'm a user, the user is always right. When I'm a dev, the user's an idiot. I'm sure you're always familiar with that. It's like being a driver. When you're driving, cyclists are awful. When you're cycling, what are these drivers on about? The reality is, in today's world, with a lot of the new technologies coming along, to be able to be in that, what I call a full stack dev scientist, to be able to be a developer and a scientist is really, really hard, actually. To have the time to be competitive as a scientist while working as a developer. And yet we know that having people who use the software, I am convinced that if people who write the software also have to use it regularly, that can only be positive. And as part of my justification for that, I ask you, if anybody here has ever tried to insert cross-references into a Microsoft Word document, you will agree with me that there is no way that anybody working at Microsoft has tried that. I swear. I mean, they would have died of embarrassment. If you're watching this on YouTube, that's my personal opinion, not belong to anyone else, please don't sue me, but it's true. The other problem, I don't know what it's like actually across Europe. In the UK, we have this issue that science exploitation and science enablement are funded completely independently. So the ability to employ someone to help develop your astrophysical software and have them time to do science, which is what we want and is best for everyone, the funding councils don't get. It's so difficult to actually do that. It really makes me quite angry. There are approaches we can take. Some of the things like user stories, there's if you don't know what that is and you want to, you can ask me in a bit, but with an agile, having a continually working product, regularly checking in with users, all this stuff that comes as part of the Agile Manifesto, I really believe helps with this. I'd also point out that there are so many things, and you'll see memes of these on the internet where people talk about agile, showing processes that are not agile at all. It's become a word that people throw around without any meaning. So you have to be careful. But at the least, right from the scratch, from the start, having a user community that you can interact with, that you can find out, are we developing what you actually want? Does this look like what you want? I think is really important. Because what users want and what as a dev we think they want are often not the same thing. And I'm sure you all know some of the horror stories about this. Of course, what user A wants and what user B wants is also not always the same thing. So that's a bit of a challenge. But there are some problems that we have to be acknowledged about as well as interacting with users. You've probably heard the claim that the shortest possible measurable unit of time is what they call the New York second, which is defined as the time between a traffic light going green and the cab behind you honking. This is not true. The shortest possible measurement of time is that between you releasing a new version of software and somebody finding a critical bug in it, which can actually violate the uncertainty principle. I don't know how this happens, no matter how much you test. I do know people who are really good at, they can walk into a room and the computers just break. If you know one of those, get them to test your software. It still won't entirely help. Users always want more as well. Seriously, the more you give, the more people want. I think that's good. I think it's really good. I mean, it keeps us in the job, but it's really good because users want to be able to do more and more science, which is great. Just remember, you don't have to, you're not anyone's slave. You don't have to give everybody what they want. Some people can be really quite demanding and aggressive. You do not have to give everybody, unless they're paying you, what they want, and certainly not all now, even when they're paying you, right? I mean, there are limits. Some things are great. Some user requests you note would come in and you thought, I wish I'd thought of that. That's brilliant. So triage is key. And again, I'm not saying this, okay? So I want you to understand you have not heard me say this, but I will just add that if, for example, you are realizing my grant is up for renewal in 6 months, I've got to write a case, and a really good idea comes up from someone, you might conceivably think, instead of doing that now, maybe I'll put that in my grant case to do for next time. Obviously I didn't just say that, but no, that's antics. But a few other things to note. You will and you should spend absolutely hours crafting wonderful user documentation to teach them how to use your tools, okay? This is advice I give to any early career researchers, especially new PhD students. One of the problems with writing documentation is like writing your first paper, is it's easy to forget how much of what you've now got your head so into is actually specialist knowledge and your readers won't understand. I think a problem that I've often seen in early, in like PhD students' first paper or even undergraduate reports is they forget that the reader doesn't know what all these acronyms they're using means. It's the same. Get someone you trust to read your documentation and see if it makes sense to them. Don't get your boss to read it. Apart from the fact that your boss never uses it, at least, my experience, he's not online and I think he'd accept this, my old boss, if I poke fun at him about this, but as I send him documentation and say, I've revised sections 1 and 2, could you read them please? And he sends me comments on sections 3 and 4, and stuff like that, The only group of people you can guarantee will never read your documentation are the users. I reckon about 90% of help requests we get could be replied by sending them this XKCD comic, but I also figure I'd get in trouble for doing it. I literally once, I had an email from the editor of a journal and said, Phil, I've got a paper that's being refereed and the authors and the referees are not reaching agreement. And I'd just like you to come in and read, don't referee the paper, just read the point and they're in dispute and give me your thoughts. And I said, okay, why are you asking me? And the reason he's asking me was because the dispute was about one of my tools. And I don't remember the exact phrasing, but it was along the lines of, there was a section in my documentation that said something like, note that you cannot use these data to infer such and such. And the authors had quoted in their reply to the referees, the documentation says, use these data to infer such and such. And it was at that level of, please somebody kill me, or better still, them. So there is a genuine, it's a frustration you can never get around. If you make it so detailed, it's impossible to misunderstand. People won't read it because it's too long. If you make it concise, people won't read it or understand it because it's too concise and whatever. People just won't read it. The other thing I'll be honest about, you have to cope with is users can be wonderful. I show this as a humorous example, but a colleague who had made quite a lot of use of my tools and been very grateful for them happened to see this book, Why Don't They Ask Evans? It's an Agatha Christie murder mystery, and saw that and thought of me being an Evans, and didn't tell me, and I just randomly found this in my pigeonhole one day as a little thank you, which was really nice. I've also had, honestly, the number of emails we get to our help desk that say, I'm learning to analyze Swift data, and I've seen your tools, but I want to learn how to do it myself. So far, so good. And I did, and I get a different result to your tools. So your tools are wrong and you need to fix them. Why aren't they working? I will say we do get plenty of them that say, what am I doing wrong? Or can you explain the difference? 99% of the time we say, did you correct for pileup? And they say, what? And you say, you didn't read the documentation. but people can be unbelievably rude. I've also, just not at all a rant here, but I went to a conference once, I'm not going to name any authors, but there was a poster there that my boss spotted. And basically it said that the Swift results don't seem to agree with this particular model. Why not? Well, we reanalyzed all the Swift data and we get different results to the online system. So the problem is the online tools don't work. Now, they hadn't come and spoken to us about that. I asked any questions, and just put this poster out at a big Swift conference saying that our tools don't work. And again, we sat down eventually and had a chat, and it, largely it was piled up. And again, they'd done their analysis wrong. And that's not just me saying, we spoke and asked them what they'd done and said, okay, that's literally not right. Here's the proof. And they went away and changed it. you think, I just find that shockingly rude. And it happens. So if you are a developer, keep a stress ball to hand and never reply immediately to emails. Honestly, I mean, seriously, by all means, write an email and delete it. Don't put the to line in, okay? If you're writing like a stress relieving email, but you've accidentally put their address in the to line, it takes one accidental slip of the fingers to click send when you didn't mean to. So to delete the to line. The other thing to tell you as a developer, your job is not to do everyone's science for them. The other category of emails we get a lot, which still make me laugh and despair, is it starts something like, hey, we used your tool to analyze this object. And in the first observation, the spectrum comes out really hard. And in the second observation, it's really soft. What's going on? And so you look at it and think, well, what could be causing that? Is there some weird background issue going on there? Was the temperature really high? Have we got a lot of hot pixels that aren't masked out? And then you realize, no, it's genuine. What they mean is, yeah, but why has my object changed spectral states? And you're like, are you asking me to write your paper for you? Because I didn't see an offer of co-authorship here. I mean, it happens genuinely. And so just remember that it's okay to decline some help requests. Say, sorry, that's something you need to talk to your PhD supervisor about, not me. Yeah. So trying to wrap up, how do we factor all of this stuff into our approach? What would be my final key points of advice? I will quantify that last line in a minute. So remember, scope is going to widen, okay? Whatever project you've got, almost definitely is going to end up doing way more than you hope for. And that's a good thing, embrace that, but plan for it right from the start. As far as possible, one of the stupid things I did, not realizing what was happening, was there were bits of code, if I'd realized, even on that very first job that I did, and I said, this is going in a module, a centralized module that other things can call, instead of it all being hard-coded into, the light code software that I wrote is still at the heart of almost everything I did. It's one of the worst pieces of code you will ever see. I desperately need to rewrite it. It's horrible to maintain, and I'm terrified to touch it because it works. Design it better from the start. Write developer-facing documentation. I'll say more in just a second. Autodocs are quite good. Sphinx, Doxygen's a good start. Give yourself a test harness. And also give yourself a test harness. And for those of you who are British and know about cult British comedy, I just at my Crichton moment, this is technically, I realize this is one issue, but it's such a big one, I thought it worth mentioning twice. Seriously, have a way of testing everything offline so that you can break anything you like without it going live. Remember that your technology is going to change. So separate your interfaces from implementation. And this has got easier over time. For example, I mean, SQL Alchemy is something some of you might have used, for example, or other object relational models. You can literally build code now where your code does not need to know what the database is. It doesn't need to know what the SQL used by that database is. So you can change one config file and switch your whole back end from MySQL to Postgres, for example, instead of having to change 493 scripts. There are all sorts of tools to do that. We've had to move, I think, originally we were using just cron to run jobs, okay? Then we moved to SunGrid Engine, then we moved to Talk PBS, then to Open PBS, and we might have to move to Slurm. And if I had one module that did all of the batch submission for you and changed one file, life would be so much better. I mentioned developer-facing documents. If anyone knows any good tools for this, I'd love to know. I think as well as writing documentation down, pictures are great. And once you've got a complex system, anything that shows how all the pieces interact would be great. And those tools exist, but they all seem to be single language. I have a structure that's made of things get triggered by procmail or by cron or by click on a website or by data getting transferred or by something else I can't remember. And I've got a series of bash scripts, Perl scripts, Python scripts, C++ programs, as well as the PHP and JavaScript. And I want something that can just draw me a map and show how it's all connected. So I know what wires I can pull out safely. If anyone knows how to do that, let me know. But if not, if you do it manually from the start, it's probably easy to keep track of. Might have mentioned this test harness. Genuinely, I mean, I say employee sysadmin, especially as things are getting more complicated. I mean, Kubernetes on its own, if you want to use that, it feels to me like you did a PhD just in that. Don't try to do everything yourself, in other words, but do factor in the fact that you're going to have to learn stuff, okay? Remember, you will not be the last person to do your job. I wish I'd learned that earlier. I mentioned developer-facing documentation. Apparently, things like work you steaming pile of elephant dung is not a good Git commit message. I mean, it was heartfelt, it was honest. I think this is what should underlie our output, but But if other people at some point, even if you're on what you think is a small project, are going to have to be involved. One of the things in the Agile Manifesto is about no siloed knowledge. There shouldn't be one person who, if they get hit by a bus, that's it, nothing works. if I'd done a better job, if I had taken a little bit more time to document things as I went along, I would have had a much easier job of handing over to the excellent person who's going to be taking over this for me than I've actually had. And lastly, I say users will do something stupid, where stupid means anything we don't expect, okay? So even if it's a brilliant idea, if we didn't expect it, clearly it's not. But generally, factor that in, okay? Make sure you have people who are using your tools for its intended reason, who can give you feedback that you can listen to, so you know what they're going to need. And just bear in mind that I really believe that lowering the bar to using any observatory or equipment is a good thing. We want to make it easy for scientists to do science, but that does come with a cost. I love this quote from Douglas Adams. A common mistake that people make when trying to design something completely foolproof is to underestimate the ingenuity of complete fools. That's in Mostly Harmless. It's the easier you make it for people to use tools, the easier it is for them to make mistakes. And I found you try putting in warning messages, hey guys, this data set you've generated needs checking because here is something that might be wrong about it. You can try to catch those. The problem is sometimes you then find, I've literally seen people saying, Swift XRT data cannot be used for such and such. And you think, what? And it's because they did something for it and they got a warning. And if they checked it, they'd have found it was fine. But it's in the warning and interpreted as, this doesn't work ever. So, you can't lose. But I think I would remind you, our responsibility is limited. If you'll forgive me, I realize it might seem a bit out of place here, but if you'll forgive me quoting the Bible for a minute, when God calls Ezekiel, he says to him, you are a watchman on the walls. If you give a warning and people don't listen, that is not your fault. If you don't give the warning and people listen, I'll hold you accountable. And that's, a totally different context, our limitation. Our job is to make the tools and to make it available for people to use and to give the information that we can. But if people don't listen to our documentation, that is not on us, okay? But we want to make things as easy to use and as hard to do something stupid with as possible, okay? So I'm going to wrap up here. I just say, I love coding, I really do. Actually, one of the great joys for me personally about having handed over some of this responsibility is that I found that I can enjoy coding a bit without the pressure anymore. I've been messing around learning how to write GUI stuff in C++ in my spare time, because that's how exciting a person I am. But, science is also fun, and everything at times, gets you bogged down, but we need try to keep it that way. Enjoy what we do. Remember that, as far as I'm aware, in most countries, force-feeding a user their own feet is not legal. I don't know that there are any laws against accidentally blacklisting their IP address. So, just say don't do that too many times. Time pressure is real. I don't know how you find it, but I personally, at the moment, feel constantly everything had to be done by yesterday. Okay, it's just life can be so stressful. It's horrible. And trying to stay on top of the to-do list and the demands of users and the bugs that have just come out, and the fact that you've turned on your computer this morning and found that your SSL certificate's expired and some bot has just sent 2,500 job requests to your system and overloaded it. And you can feel like everything has to be done now and there's no time to document it properly and so on. Genuinely, you're only hurting yourself by not doing that. So spend the time now to save it in the future. But remember, the software that we produce is fundamental. Projects cannot achieve their goals without them. And it's not a thankless task. People are aware and do appreciate the work that everyone, who's involved in that does. And so take pride in what you do as well. And don't feel, it's easy to feel a little bit, what can I say, second class when you're looking at someone who I've spent most of my career comparing myself to my contemporaries who were 100% science postdocs and have produced 5 times as many papers as me, got way more grants than me, and are now way more senior than me. And that may just be because they're all better than me. Some of them, like Antonio, genuinely are, but no, really. But actually, you are doing your job and take pride in it. And I'm going to stop there because I think I'm way out of time.